Linear displacement is analogy with angular displacement. Linear acceleration is analogy with angular acceleration of omega. Linear acceleration is analogy with the angular acceleration. So we can apply the kinematic equations in the linear motion. We can also write down the kinematic equation in rotational motion by using the analogy. Okay, this is the introduction of the rotational. Then later on, we move on to the topic of torque. Torque is actually a vector quantity. Torque is defined as lever arm crossed with the force of action. SI unit for torque is Newton meter. So torque, it will cause the rotational motion either in clockwise direction or anti-clockwise direction. In a universal sign convention, usually we assume that anti-clockwise direction is positive, the rotational motion is positive, and for the clockwise direction, then the torque has a negative value if it is rotate in clockwise direction. The condition, call it as equilibrium. When the system is at equilibrium, the summation of the force is always equal to 0. So this is one of the conditions of equilibrium. So other than this equilibrium, summation of F equal to 0, we have another second condition for equilibrium, that is summation of torque is equal to 0. For example, I have a seesaw, okay, which is a plank, and this plank is symmetrical and the mass is distributed uniformly. Center gravity of the plank is actually located exactly at the center of, okay, for example, the seesaw is placed on fulcrum. Firstly, I draw out a free body diagram on the system, which consists of the plank and Susan's and also Peter. So the free body diagram would be the weight of Susan, m1g, for example. The weight of Peter is m2g. The weight of the plank, actually we draw it from the center gravity of the plank. Right? So now, center gravity. So center gravity is usually located at the center if the mass of the object is distributed uniformly. Now, if Susan is sitting at the distance x1 from the axis of rotation, so I assume that here is the axis of rotation for the system. And Peter is sitting at the location of x2 from the axis of rotation. Another one is the normal exerted on the plank due to this fulcrum. The forces, m1g, weight of the plank, m2g, and the normal are all vertically, either upward or downward. So summation of F along y component is equal to 0. There's no force along x component. Right? So if I assume that up is positive, down is negative, so I add up all the forces together, I will get m plus negative m1g plus negative weight of the plank plus negative m2g is equal to 0. Okay, this is the first condition for equilibrium. Second condition for equilibrium is summation of torque is equal to 0. For the equilibrium, summation of torque is equal to 0. You must know as well where is the axis of rotation. For this seesaw here, very obvious axis of rotation is located on top of the fulcrum. Let's find out what is the torque produced due to Susan. So m1g, the weight of Susan, will tend to rotate the plank in the anti-clockwise direction. Okay, because axis of rotation is here. Anti-clockwise direction means it has a sign convention of plus, and therefore the torque produced due to Susan's will be RF. R crossed with F. R is x1. F is m1g, right? So we also know that R cross F in torque is actually equal to RF sine theta, where theta is the angle between R and F. Okay, so happen m1g is a gravitational force. The lever arm is x1. The angle between x1 and m1g is 90 degree. 90 degree, and therefore sine 90 is 1. So you can just ignore the sine 90. Okay, you can just write x1 multiply with the gravitational force of m1g. Okay, the other one is Peter. The weight of Peter is m2g, so m2g is directed downward. Axis of rotation is at this point. The force due to Peter tends to rotate in this direction, and therefore the sign convention of the torque will be negative plus negative. R is x2, lever arm is x2, and the gravitational force is m2g, right? Is equal to 0. when the force is intersect with the axis of rotation, the torque produced is equal to 0. So happen, normal force is acting at the center of gravity. And the axis of rotation also at the point of center of gravity. And therefore, the torque produced due to the normal force is equal to 0. So by using these two equations, equation 1 and equation 2, you may find out the unknown that you need, right? Center of gravity. So center of gravity will be located exactly at the center of the object. If the object is symmetrical and the mass is distributed uniformly along object. Right? So center of gravity, we use a CG to represent it. So center of gravity can be calculated by using the sum of moment divided by sum of the weight. So if you look at the system, consists of the weight of the bar and also consists of the weight of the block. So the sum of the weight will be W1 plus W2. And sum of moment. So moment is a product of force and also the distance, right? If the axis of rotation is here, so the force means the gravitational force. Gravitational force of the bar is W1 multiplied with x1. So you will get W1 x1. Then the gravitational force due to this block is W2. So I'm using W2 multiplied with x2. Sum means you just add up together, right? That is how you find out the center of gravity. If I have an object, this is a shape of the object, and I place the object along the x-axis and y-axis. I assume that the object is rotated at O, origin. Here is the axis of rotation, right? And I'd like to determine where is the center of gravity for this object. Maybe the object consists of a few main mass. Okay, the mass of the object, okay, maybe it's here, M1. Okay, the other mass is M2. The other mass is M3 is here. The location of M1 will be then equal to x1, y1. Coordinate of M2 is x2, y2. Coordinate of M3 is x3, y3. Okay, these are the coordinates for the system or for the object. So of course, this object consists of more than 3 particles. I just simplify the object to make it as 3 particles. These 3 particles contribute to the object, which has the unknown shape. The gravitational force due to these 3 particles will be always directed downward. So I have M1G here, M2G here, and M3G here. So to determine the center of gravity, for example, center of gravity is located here. What is the coordinate for the center of gravity? So since M1 consists of x1 and y1, same as M2 and M3, so this center of gravity should consist of coordinate x and coordinate y as well. So consists of x coordinate, center of gravity, and center of gravity for the y coordinate. So the formula should be summation of mx divided by summation of mi. So y coordinate will be summation of mi yi divided by summation of mi. I stand for the number of particle. This 1, 2, 3, right? So summation of mixi stand for, you have to add up the product of m1x1 and m2x2 and m3x3. So if you're more than that, you have to add further and divided by m1 plus m2 plus m3. This is x coordinate. So same as y coordinate, you just add up the product of m1 y1 plus m2 y2 plus m3 y3 plus dot 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 divided by the total mass m1 plus m2 plus m3 and dot dot dot. Okay, that is how you get the center of gravity for the system which consists of 3 particles. General expression, sum of moment divided by sum of weight. Moment means a product of F and R. So F in this case here will be gravitational force. So R means, I put it as x first. So sum of Wx divided by sum of weight. So we know that weight is actually the gravitational force, mg. So mg. So multiply with x divided by summation of W is mg. Okay, and therefore G and G is actually a constant, so you may just cancel off, and that's why you get back summation of mx divided by summation of m. So actually it's the same. Newton's second law. Summation of F is equal to ma. Right? So this F means the net force. Net force is always equal to the product of m and a. To make it simplified, I refer to force F. Net force is equal to ma. Okay, and now I multiply R on both sides of the equation. So Fr equal to MAR. So product of force and R is actually torque, right? The magnitude of torque is equal to RF sine theta. Okay, if R and F are perpendicular to one another, and therefore torque is equal to RF only. In a linear motion, we have the linear acceleration of A. In the rotational motion, we have the angular acceleration of alpha. A equal to R alpha. It's just like S equal to R theta, V equal to R omega, A equal to R alpha. So here, A equal to R alpha, and eventually I will get the torque as mR square alpha. This mR square alpha, I call it as I alpha, and this I, we name it as moment of inertia. This one is also called as Newton's second law for rotational motion, right? It name it as Newton second law for rotational motion, right? So which means F is analogy with torque, A is analogy with alpha, and M is now analogy with moment of inertia. Mass here, in a linear motion we do mass, but in a rotational motion we don't look at mass, we look at a term called it as moment of inertia. We refer to this list. This is the moment of inertia for various shape of object. If you have a thin loop which has a radius of r, then the moment of inertia would be the mass of the loop multiplied with the radius squared to get the moment of inertia. Solid disc, for example, which has a radius of r, and the moment of inertia, we use another formula, half mr squared. The moment of inertia of a sphere is 2/5 mr squared. Uniform rod, the axis of rotation is at the center, then the moment of inertia is 1/12 ml squared, where L is the length of the uniform rod. If the axis of rotation is at the end of the rod, then the moment of inertia change to 1/3 ml squared. So based on this list, you can see that whenever you change the shape of the object, we are going to use a different formula to find out the moment of inertia. Whenever you change the axis of rotation, you use a different formula to calculate the moment of inertia as well. Right? So which means when you want to find out the moment of inertia, firstly, you have to know that what shape is the object and where is the axis of rotation. Then only you can find out the moment of inertia. Okay, and the unit for the moment of inertia, SI unit is kilogram meter square. In general, moment of inertia is a summation of mr squared. This is moment of inertia. Linear momentum is a product of mv. In a rotational motion, we can find out angular momentum. So you use the analogy as well. So for angular momentum, we use a symbol of L. So since the linear momentum is the product of mv, so we know m is analogy with I. So this one is analogy with L. This one is analogy with omega. Therefore, angular momentum is the product of I omega. So we can also apply Newton's law. F is equal to the rate of change of momentum. In a rotational motion, torque is equal to the rate of change of angular momentum. F is the rate of change of momentum. That is Newton's second law. So in a rotational motion, torque is the rate of change of angular momentum. Moment of inertia I is equal to summation of mr squared. Dancer put in her arm, R is reducing. R is reducing means it tends to reduce the moment of inertia. So once you reduce the moment of inertia, so what happened? So if you refer to the conservation of angular momentum is defined as I omega. We have one principle, call it a principle of conservation of angular momentum. Means momentum initial is same as momentum final. So momentum initial means I initial omega initial is equal to I final omega final, which means angular momentum is a constant. So while the dancer pull in her arm, she's trying to reduce moment of inertia. So when the moment of inertia is reducing, L is always a constant. So while she's reducing the moment of inertia, speed will be increased. The reason the dancer pull in their arm is to reduce the moment of inertia, increase the angular speed, increase the omega. That is the reason.